Welcome to our Quantum Deep Dive. Today we're taking a really fascinating plunge into one of the most counterintuitive yet absolutely foundational principles of the quantum world. I'm talking about the No-Cloning Theorem. And this deep dive is inspired by a really compelling essay from Jorgo Schneeppert titled No-Cloning Theorem and Fundament der Quantenmechanik. Our mission today, to unpack why you absolutely cannot make a perfect copy of an unknown quantum state. Sounds simple, but the implications are huge. We'll explore what this means for things like secure communication, even the future of computing itself. Okay, so let's unpack this a bit. Imagine you've got like a digital photo on your computer, maybe a document. You can copy that file endlessly, right? Hit cheat trill plus C, cheer
right,
plus V.
spend it, upload it, make a million copies.
Exactly. And the original's untouched. That's, classical information. That's how we usually think.
Correct.
But in the quantum realm, things get really weird really fast.
Mm-hmm. They really do. Mm-hmm. And what's so fascinating here is the no-cloning theorem. It tells us, point blank, it's fundamentally impossible. You cannot create an exact, perfect duplicate of an arbitrary, unknown quantum state.
And this isn't just like, oh, our tech isn't good enough yet.
No, not at all. It's a deep physical law. It was independently formulated, proven back in 1982. Scientists like Wooters and Zurich and also Dux, they nailed this down. And the core reason, well, it lies right in the heart of quantum mechanics itself. See, a quantum state often isn't just a simple yes or no, on or off. It exists as a superposition of possibilities. Kind of like a coin spinning in the air. It's both heads and tails until it lands.
Okay.
And any attempt to measure or observe that state, to figure out exactly what it is, that inevitably forces it to collapse. The spinning coin has to land on heads or tails.
Ah, so the act of looking changes it.
Precisely. You can't just peek at that spinning coin, learn its exact heads-tails mixture, and then replicate it. Because the peeking itself alters the original. That interaction makes flawless duplication impossible without messing up what you started with.
Right. That makes a certain kind of conceptual sense, observation changing things. But how does that fundamentally stop copying? Couldn't you just measure it, get a result like heads, and then just create a new head state? What's the actual quantum rule that slams the door shut?
That's a great question. It takes us into the math of it all. In quantum mechanics, a system's state, an electron spin, a photon's polarization, a qubit, isn't just a simple value. It's described by what we call a state vector. Think of it as an arrow pointing in a specific direction in a special mathematical space, a Hilbert space.
Okay, Hilbert space. Got it.
That's right. And this space lets us represent all those possibilities, the superpositions. For a qubit, the basic unit of quantum info, its state might be a mix written like POI, OS, PLUSOA, 1. Here, A and VAR are these complex numbers, basically telling you the probability of finding 0, arrow, 1 when you measure it.
Probabilities, right.
Now, when you do measure it, that nice superposition collapses. Poof. It falls into one of the basic states, 0 or 1A. And the chances of getting 0 or 1A depend on those A and VAR values specifically. A squared and bus squared. But here's the kicker. Unless you already knew on perfectly beforehand, which you don't, for an unknown state you want to copy, the measurement outcome is probabilistic.
So you get a result, but you might have destroyed the original superposition to get it.
Exactly. The measurement almost always changes that original state unpredictably. You can't just read it and recreate it faithfully.
And this isn't just a concept, you're saying. There's actual math, a proof that shows this. That's pretty amazing. Not just a guideline, but a hard mathematical limit.
Absolutely. The proof is quite elegant, actually. It revolves around this idea of a universal unitary operation. In quantum mechanics, unitary basically means a transformation that preserves all the quantum information. It's perfectly reversible, like running a movie backward.
Okay, reversible, like no information is lost.
Correct. So the proof asks, could there be such a perfect information-preserving quantum machine, a unitary operation that could copy any unknown quantum state you feed it? So let's connect this to the bigger picture. Imagine this hypothetical perfect quantum copier. You give it a simple 0 state, sure, it gives you 2 zeros. Give it 1 yeah, you get 2 1s. That part seems fine.
Seems logical.
But what about a superposition? That mix, at plus Beria. If this copier was truly universal and perfect, you'd expect to get 2 identical copies, right? So at plus OR for the first and at plus OR for the second. But the mathematics of unitary operations just doesn't allow that. It breaks down. When you apply the rules, the kind of operation that copies 0 to 0, 0, and 0, 1, 0, when applied to the superposition RO plus BRO, it produces a state like A² plus BT01.
Wait, that looks different.
It is different. It's an entangled state, not two separate copies of the original superposition. If you had two copies, the full state would look like A² plus YR, A plus GOR plus OR plus Y polaro, which expands out to include terms like A² and BT10.
The cross terms.
Exactly. Those cross terms just aren't generated by the simple copying operation. That algebraic mismatch right there in the math proves a universal copier. Like that just can't exist. So fundamentally, because a state is often unknown and measuring changes it, you can't duplicate it without loss or disturbance. It really highlights how quantum information is kind of protected. It resists perfect replication.
Wow. Okay. So this isn't just some theoretical quirk. It has huge real-world consequences. You mentioned communication and computing.
Sure.
So why should you listening care about this? It feels like it's not just about what we can't do, but maybe what this impossibility enables.
That's a great way to put it. It really does shape the landscape. First off, quantum communication. The no-cloning theorem is basically its security guard. Think about classical data. Someone can copy it perfectly, maybe without you ever knowing.
Yeah, eavesdropping online.
Right. But with quantum encoded messages, any attempt by someone, let's call her Eve, to intercept and copy that message, it inevitably disturbs the quantum states. It leaves a detectable trace.
Like footprints in the snow.
Exactly. The communicating parties, Alice and Bob, can check for these disturbances and know if someone was listening. This is the foundation of quantum security. Eve simply can't make a perfect copy without revealing herself.
Okay, so how does that work in practice? Is there a system that actually uses this?
Yes. A classic example is the BB84 protocol, named after its inventors, Bennett and Broussard. It's for quantum key distribution, sending a secret key securely. So Alice sends qubits to Bob, but she prepares them in randomly chosen bases. Think horizontal-vertical polarization, or maybe diagonal polarizations, plus 45 degrees. Random choices.
Okay, random base.
Bob, on his end, also measures them using randomly chosen bases. He doesn't know which bases Alice used for each qubit. Afterwards, they talk publicly not about the results they got, but just about the bases they used for each measurement.
Just the settings, not the answers.
Precisely. They discard the results where their bases didn't match. Now, if Eve tried to intercept the qubits mid-flight, she has to measure them to try and copy them. But she doesn't know Alice's random basis choice either.
So her measurement is likely to be in the wrong basis.
Which disturbs the state. So when Alice and Bob later compare a small sample of the results from the qubits where their bases did match, if Eve was listening, they'll see more errors than they'd expect just from noise. Boom! Intrusion detected.
Because Eve's copying attempt, thanks to no cloning, inevitably messed things up.
Exactly. It provides a fundamental security layer that classical cryptography just doesn't have.
Okay, that's security sorted. But what about quantum computers? It sounds like a massive headache if you can't copy states. Classical computers copy stuff all the time for backup, error checking.
It is definitely a challenge, a big one. Classical computing relies heavily on redundancy, just making copies. Need fault tolerance, copy the data. Need to run parallel tasks, copy the input. Quantum computers just can't do that with the quantum states themselves. You can't just hit Qunner plus C on a qubit superposition for backup. It forces completely different thinking about error correction and how computation even proceeds.
So things like debugging must be incredibly hard then. You can't just pause and inspect the state without destroying it. Or even just spreading a calculation across different quantum processing units.
You've hit the nail on the head. Debugging is tough. You can't just take a snapshot of the quantum state mid-calculation without collapsing it, potentially ruining the very thing you're trying to fix.
Yikes.
Yeah. So people are developing clever methods like weak measurements, trying to get partial information without causing a full collapse, and distributing workloads. Also tricky. You can't just farm out a piece of the quantum state. This is why quantum error correction is so vital and so different. Instead of simple copies, we use codes, like the famous Shor code, which cleverly distribute the information of one logical qubit across many physical qubits.
Entangling them.
Exactly. Often using entanglement. For instance, encoding one qubit state across, say, 9 entangled physical qubits. This redundancy allows you to detect and correct errors on some of the physical qubits without needing to know or copy the original logical state perfectly.
So you protect the information by spreading it out, not by making direct copies.
Precisely. It sidesteps the no-cloning theorem by encoding rather than copying.
Okay, and if we can't clone, How do we get quantum information from A to B over long distances? We can't just copy-paste it into an email. How does a quantum internet even work?
Right, another great question. The answer is quantum teleportation.
Okay, that sounds like science fiction.
It does, but it's real. Though maybe not quite like Star Trek. It's not beaming objects. It's about transferring an unknown quantum state from one location to another without physically moving the particle that holds the state.
How does that work then?
It relies on pre-shared entanglement. Imagine Alice and Bob each have one qubit from an entangled pair. They're linked, no matter how far apart. Alice wants to teleport the state of a third qubit she has. She performs a special joint measurement on her qubit and the one she wants to teleport.
Yeah.
This measurement actually destroys the original state on her qubit.
Okay.
It yields some classical information, just a couple of bits of measurement results.
Classical information. Like regular zeros and ones.
Yep. She sends those classical bits over a normal channel, phone, internet, whatever, to Bob. Bob then uses those classical bits as instructions to perform specific operations on his entangled qubit.
And that reconstructs the original state.
Miraculously, yes. Bob's qubit is transformed to the exact state that Alice's original qubit was in.
But the original was destroyed.
Exactly. Because the original state is destroyed during Alice's measurement, no copy was ever made. Information was transferred, not cloned. It respects the no-cloning theorem perfectly.
That's incredible. It really shows how different quantum information is.
And it leads us to something related, actually. The no-deleting theorem.
No deleting. So you can't perfectly erase an unknown quantum state either.
That's right. Just like you can't perfectly copy one. If you think about it, copying and deleting are kind of related to creating and destroying information. And if we connect this to the bigger picture again, quantum mechanics, with its unitary evolution, implies a deep conservation of information.
Conservation, like energy conservation.
In a sense, yes. Quantum information can be transformed, moved around, hidden in correlations, entangled. But it's never truly created from nothing or destroyed completely. This is fundamentally different from classical information, where we think we can just hit delete. Quantum information seems much more persistent, more physical.
Okay, so perfect cloning is impossible. Are there any loopholes, any ways to get close? Or maybe situations where it is possible?
Well, loopholes might be too strong a word, but there are nuances. While exact universal cloning is impossible for an unknown state, you can do approximate cloning.
Approximate, so like a fuzzy copy.
Sort of, yeah. You create a copy that's not perfect, but it has some similarity, some fidelity to the original. There are theoretical machines, like the optimal quantum cloning machine, the UQCM, developed by Bushik and Hillary back in '96, that produce the best possible imperfect copies allowed by quantum mechanics.
So you get something, but it's not perfect.
Right. Then there's also probabilistic cloning. Sometimes you can get an exact copy, but only with a certain probability of success. This usually requires some prior knowledge about the state, like knowing it belongs to a specific, limited set of possible states, not a truly arbitrary, unknown state. And there's another important clarification. If the states you're dealing with are orthogonal.
Orthogonal, like fundamentally distinct.
Exactly, like the basic states 0A and 1A. They are perfectly distinguishable. If you know you have either a 0 or a 1A, you can measure it, find out which one it is, and then create as many copies as you like.
Oh, okay.
The no-cloning theorem really bites when you have those superpositions, the Isotopes-Bonnet type states, where the state is an unknown blend and measurement cost is a choice. That's where the impossibility lies.
Right, that makes sense. So looking ahead then, what are the big challenges, the open questions? Where does this constraint push quantum technology next?
Well, a huge area is definitely developing those alternative information transfer methods. Since we can't just copy-paste quantum data, building things like quantum repeaters is crucial. These are needed to extend quantum communication over long distances, combating signal loss without violating no cloning. Building a practical quantum internet relies heavily on cracking this.
Big engineering hurdles there, I imagine.
Massive ones, and theoretically, there are some really mind-bending connections being explored. Some physicists are looking at links between the no-cloning theorem and quantum gravity. Could this information constraint be tied to the very fabric of space-time?
Whoa, okay, how?
Ideas like the holographic principle, which suggests information in a volume of space might be encoded on its boundary, seem to resonate with no-cloning's implications about information not being arbitrarily creatable or destructible. It hints that information limits might be fundamental to reality itself. And looking further into the future, no cloning will just keep shaping things. It's the driving force behind the need for ever more sophisticated quantum error correction for reliable quantum computers. Concepts like topological quantum computers are partly motivated by finding ways to encode quantum information inherently robustly, less susceptible to errors that you can't just copy correct.
Making the information naturally resilient.
Exactly. And it even connects to the thermodynamics of information, understanding the energy costs and fundamental laws governing information processing at the quantum level. It forces us to ask really deep questions about what information is.
What a fascinating journey. So we've really seen how the no-cloning theorem, stemming directly from the mathematics of quantum mechanics, is far more than just a rule saying no copying. It's the bedrock for quantum security like BB84. It forces entirely new designs for fault-tolerant quantum computers. And it even makes seemingly sci-fi concepts like quantum teleportation not only possible, but necessary. It truly reshapes our understanding of information.
It really does. It highlights that quantum information isn't just abstract data, it's a physical resource. Finite, unique. It can't be endlessly duplicated like classical bits, nor can it be perfectly erased. That fundamental difference forces us to grapple with the nature of information in a much deeper way, opening up challenges, yes, but also incredible new possibilities.
Well, we hope this deep dive into the no-cloning theorem, drawing heavily on Jurgo Schneppat's insightful essay, has sparked some aha moments for you. It's one of those ideas that really shifts your perspective on the quantum world. To explore more about these fascinating topics, you can definitely visit schneppat.de. Thanks so much for joining us for this quantum deep dive.